shall continue. And all right, so let's talk about when you would want a type 1 error or type 2 error. Okay, not when you don't want these errors, but when you would want a large alpha or small alpha. Okay, so alpha is probability of type 1 error, beta is the probability of type 2 error. If you pick a large alpha, you're more likely to commit type 1, but less likely to commit type 2. And if you pick a small alpha, you're less likely to commit type 1, but more likely to commit type 2. Okay, all other things equal. So I'm just going to give you two examples where whether you want large alpha or small alpha is going to be different. Okay. All right, so or I should say smoke detector. Okay, what's the job of a smoke detector?
Detect smoke.
Okay, detect smoke, right? But why do we care if it detects smoke or not? It's supposed to alert you if there's a fire. Okay, that's the critical thing. Okay. You can imagine if you were. Okay, so smoke detectors are just machines, right? So what if we lived in some magical land, okay, but we had smoke detectors, right? And we shrunk little people down into living into a smoke detector. And their job is to sit there and they smell the air, and if it smells like smoke, they're going to hit the alarm and say there's a fire. Okay. In this case, what would the null and alternative hypothesis be? So remember, when we gather evidence, we use the evidence to support which of the hypotheses. Okay, about the answer. Okay, so the evidence is always used to support the alternative. Okay, we can never use evidence to support the null. It's either the evidence supports the alternative, or we don't have enough evidence to support the alternative. Okay, or it's evidence to reject the null or not reject the null. Okay? So in this case, the presence of smoke is our evidence is used to support the alternative. So the alternative is there is a fire. And the null is there is no fire. Okay. And so, little person living in the smoke detector is spends the day sniffing the air, and they smell smoke. Okay. So, if you were the company, okay, and you are training people to live in the smoke detectors, okay, what would you tell them? Would you say, okay, when you smell smoke, you're going to say, okay, there's always a possibility that there's no fire, but you happen to smell smoke. Okay, there's always that possibility. Or, I mean, it's a possibility that the house is not on fire, but you're still smelling smoke. Okay, would you say, you know what? Don't sound the alarm until you're absolutely sure that there's a fire, that the smoke is choking you and you're absolutely sure there's a fire? Or would you say, you know what, as soon as you're a little bit suspicious that there's a fire, sound the alarm because it's better to be safe? What are you going to say? You're going to say it's better to be safe, right? So in that case, are we picking a large alpha or a small alpha? We're picking a large alpha, okay? So here, we choose large alpha, okay? Why? Because in this situation, what does it mean to commit a type 1 error? A type 1 error for the smoke detector is what?
say that there's no fire, but there is a fire?
I think just the opposite.
Oh.
Type 1 error is rejecting the null when the null is true, okay? So here is, there is no fire, but you rejected it, but you sounded the alarm. Okay, that's a type 1 error. False alarm. Yes?
What does fire alarm / smoke detector mean? Are we saying given smoke detector?
Oh, no. Whatever. I'm just, whatever the thing in the ceiling, that's a smoke detector, or some people might call it a fire alarm. I don't know.
AKA. Oh.
Also known as, okay? Smoke detector equals fire, I don't know, whatever, okay. Your homeowner's insurance rate is lower if you have a professional smoke detector system, okay, like one that's powered by the company, not batteries or something. You know, because it's more reliable. Okay.
Wait, really?
Well, it depends. If you have like ADT or something, and they put in smoke detectors and stuff, your rate will go down.
Good to know.
Okay, type 2 error. What's a type 2 error in this situation? Okay, well just read type 1, and type 2 is going to be not the opposite, but whatever the converse. Type 2 is there is a fire, but no alarm. Okay, that's a type 2 error. Because this type 2 is you did not reject the null. That's no alarm. No alarm is not reject the null. But the null is false. Okay. Type 2. You didn't reject the null, but the null is false. That's a type 2 error. So in this situation, which error is worse than the other? Type 2. Type 2 is far worse than type 1. Type 1, it's annoying when this happens, but type 2 is tragic. So in this case, we choose a large alpha when type 2 is worse than type 1. 2 is worse than type 1. That's why you should choose a large alpha. Okay. Can you think of any situation where the type 1 error is worse than the type 2?
You could like accuse someone of something, but they didn't do it.
Yeah.
What about death penalty?
Okay, yeah, death penalty cases are just our justice system. Okay, this is my go-to example. So at least in the United States, who was one of the founding father that said it's better to let 10 guilty men go free than imprison an innocent man? There's somebody, right? Somebody. All right. Okay. So we'll say justice system. Huh?
Clearly nobody pays attention back then.
I know. It's too bad. Although they'll read the Constitution. Okay. We've got the null hypothesis and the alternative hypothesis. Okay. So in the justice system, we say the onus of proof falls on which side?
Prosecutor.
The prosecution. Okay. So if there's no evidence, you just say there's no evidence, the defendant goes free, right? It's up to the prosecution to present the evidence to convict the defendant. Okay. I mean, now both sides will present evidence and stuff, but the onus of proof falls on the prosecution. So, what's our null and what's our alternative hypothesis? We're using evidence to support the alternative. So the alternative would be defendant is guilty or not guilty? Guilty. That's the alternative. And the null hypothesis is the defendant is not guilty. So what does it mean to commit a type 1 error?
Someone's guilty when they're not.
So type 1 error is you've rejected the null hypothesis. So the jury says we find the defendant guilty when the null hypothesis is actually true. Okay? So you convicting an innocent person. Okay. And type 2 error that would be acquitting a guilty person. That's the right word, right? Acquit. Okay, that would be a type 2 error. You did not reject the null when the null was false. So, you know, sometimes type 2 errors happen in our justice system. Often happens with like high profile cases and things like that. It's that lady on CNN, Nancy Grace, she gets all angry when that happens. But you know, sometimes it happens. But the way our justice system is set up, it was created thinking that type 1 error is worse than type 2 error. Okay, and I would agree with that. All right, and you know, and this is one of the biggest arguments against death penalty or using the death penalty is that committing a type 1 error is a very bad thing, and the fact that there's even a possibility of committing a type 1 error is reason to do away with the death penalty. Okay, people will argue both sides, yes or no to that. So in this case, we would want large or small alpha? Small alpha. So small alpha when type 1 is worse than type 2. Okay. And they actually say this. They actually say this. Actually, both of these things, smoke detectors or fire alarms and the justice system, they both tell you whether when they have large alpha or small alpha. Okay? So in the justice system, they actually do say use a small alpha. They don't use those words. But what do they charge they tell the jury, what do they say? Beyond a reasonable doubt, or beyond a shadow of a doubt. They say, make sure that the evidence presented to you leads you to believe beyond a reasonable doubt that the defendant is guilty before you say the defendant is guilty. Okay? So that essentially what they're saying is use a small alpha here. Make sure you're absolutely sure before you reject the null hypothesis. Okay? So they do tell you that, just not. No, they don't say, make sure you use a small alpha in your decision making. Okay? Over here for a smoke detector, okay, actually more common with carbon monoxide detectors, okay. With carbon monoxide detectors, a lot of the instruction manuals will say, we made our carbon monoxide detector to be extremely sensitive, okay, because they want to, because it's odorless and it'll kill you in your sleep and things like that. So they want to make sure that the alarm goes off if there's any trace of carbon monoxide. But they'll say, like, we made it extremely sensitive, so sometimes the alarm will go off and you're not in any danger. So if the alarm goes off, hit the reset button, wait an hour, and if it goes off again in an hour, then leave the house. But if it doesn't go off, then you're probably fine. Okay? So the instruction manuals will actually say, we've made this really sensitive, meaning it's the detector is ready to reject the null hypothesis at the drop of a hat, really, okay? Alright, and so, you know, as if you ever do research and you get to choose which alpha you want to use, then you can keep this in mind, okay? Or if you're reading research papers and they'll talk about, they may or may not talk about the significance level that they used, but you can, at least you have that perspective in mind. I forgot to mention, when talking about the one-sided and two-sided tests, or directional and non-directional tests, so just going back to that, directional versus non-directional, or one-sided versus two-sided. And I've got to hurry up. Okay. You need to decide whether or not you're going to use a one-sided or two-sided test before gathering your data, okay? So as the researcher, you decide which type of test you will use before gathering your data. Because the nature of the non-directional test is that you double the tail probabilities, a lot of times non-directional tests will give you larger p-values than directional tests. Not always. It doesn't happen when the directionality check doesn't line up. Okay, but a lot of times the non-directional tests will give you p-values double that of the directional test. Okay, so often, not always. Non-directional tests or two-sided tests So sometimes people are tempted to look at the data and then decide, I'm going to use a directional test rather than a non-directional test, okay? And if you, and sometimes it's enough where using a directional test creates a significant p-value, one to reject the null, where a non-directional one doesn't. And so sometimes people are tempted to do this, but that would be considered dishonest.
Is this the same as one-tailed and two-tailed?
Yeah, one-tailed and two-tailed, or one-sided.
I thought you're like not. I thought one-sided are kind of considered like bogus for a lot of research, or for most research. Like they're not respected.
It depends. It depends. Yeah, and maybe also for this, partially for this reason, okay? Because one-sided tests can be used to artificially half a p-value sometimes, okay? And so people are a little bit more wary of them. Because maybe the p-value is 3% when it's one-sided, but then if it's two-sided, it would be 6%, right? So then, what to do? I have two big things to cover in the last 40 minutes. All right, so with a t-test, we're comparing two groups, and we say, do we have evidence that they have the same means or different? Okay, right? We also did the same thing when we created confidence intervals for a difference in means. Okay. And it turns out that mathematically, they're the same thing. So why do we bother learning them? Well, it's the idea behind hypothesis testing can be useful for the future. But okay, so confidence interval for a difference between means will produce the same conclusion for an equivalent two-sided or non-directional or two-tail t-test. So a 95% confidence interval for is equal. You can swap the results of this with a t-test with significance level 5%. Okay. A t-test with alpha equal to 10% would be equivalent to what?
90.
A 90% confidence interval, okay? And so you figure out the pattern from there, okay? So 90% CI, t-test with alpha equal to 10%, okay? And 99% alpha 1%, so on and so forth. Okay. Let's try a few logic puzzles. I don't know about puzzles is the right word, but let's try a few logic problems, okay? And you're going to see a couple of these on next week's quiz. Okay, so if I conduct a t-test with alpha equal to 5%, okay, and find evidence let's get rid of the word there because it's going to sound funny. Okay, so let's say I conduct a t-test with alpha equal to 5% and find evidence of a difference between the means. Between mu1 and mu2. Okay. And this is a two-sided test, two-tail test. So let's say that happened, okay? If I conducted the same test, okay, use the same evidence, same everything, but if I used alpha equals 10%, would I make the same conclusion or not? So at alpha equal to 5%, I find evidence of a difference between means.
Yes.
Yes, okay. So why do you say yes?
Because it's easier.
It's easier? Okay.
No.
Yeah, okay.
It
Well,
includes all the
yeah, okay.
results.
So this, what does this statement mean about my p-value? What does it suggest about my p-value?
Smaller than 5%.
Whatever my p-value was, it's smaller than 5%. So this implies that my p-value, I don't know exactly what it is, but I do know it's smaller than 5%. Alright, so if I redid the test with alpha equal to 10%, is my p-value smaller than alpha? Yes. Okay, because my p-value is smaller than 5%. It's surely smaller than 10%. Okay? So if I redo the test at 10%, then I will reject. I wanna make sure that's okay with everyone. What if I did the test with alpha equal to 1%? Do I reject or not reject?
We don't know.
You don't know, you can't tell. For one, we do not know if the p-value is less than 0.01 or not. So here we can't tell. Okay, so continuing on here, so saying the same thing. If I conducted a t-test with alpha equals 5%, let's say I find evidence of a difference. Okay, would a 95% confidence interval contain 0 or not?
No. Wait.
Okay, so what was the conclusion I made up here? I have evidence of a difference between mu1 and mu2. How do we decide if there's evidence of a difference between mu1 and mu2 when we're using a confidence interval? Yeah, so if it doesn't contain 0, there's evidence of a difference, right? So here, if I find evidence of a difference here, I should find evidence of a difference here. So I'll write that. So I found evidence of a difference with a t-test. So our confidence interval will also show evidence of a difference. Which means so the confidence interval will not contain 0. Is this okay? Alright. What about a 99% confidence interval? Would that contain 0 or not? You don't know. Answer? Don't know. Okay. What about okay? So just think of what is the equivalent t-test, and then what would happen there? You can make a conclusion. Yeah. Are these okay? Alright, so you'll see something like this, okay? Similar, but not exactly the same. I'm going to take a little jump in the book. The book covers something else at the end of chapter 7. We're going to actually skip that for now. We'll come back to it later. And I'm going to jump into chapter 8. Okay? But we're only going to do the first chapter of chapter 8. So chapter 7 looks at numeric responses with categorical variable distinguishing group 1 from group 2. Okay. And in chapter 7, the groups were independent. So what happened to the toluene group should have no effect on what happens to the control group, or what happens to this group should have no influence on the other group. Those groups were independent. In chapter 8, we're looking at what we call paired data. Okay? Paired data as opposed to independent data. So in paired data, we're interested in the difference between, the first group of measurements and the second group of measurements, but the each result is linked to each other. The results are linked. Okay. So let's just try an example here. Okay. So let me just say paired data, the data between the two groups, the data between the groups Alright, so let's so a lot of times before and after measurements are is like the perfect example of paired data, before and after. So let's say some company said, hey, we've got this miracle weight loss pill. Okay. If you ever hear of miracle weight loss pill, they're probably not for real. But let's say there was one on the market, okay, so they show we've got before weight and after, okay? And so let's say they say, and they're like, okay, but it's not magic, all right? But it is a miracle weight loss pill. You take the pill, and you take the pill for a week, you're gonna lose about 5 pounds. Okay, so that's what they say. All right, so let's say somebody weighed 190 pounds, and after taking the pill, they now weigh 185. And let's say somebody weighed 220, and after taking the pill, they weigh 214. And somebody else weighed 140, and after taking the pill, they weigh 136. And someone else, they started taking the pill at 160, and afterwards weighed 155, and someone weighed 240, and afterwards weighed 230. Okay. Looking at this data, so this is person 1, 1, 2, 3, 4, person 2, so on and so forth. Okay. Does it seem like the weight loss pill works? Does the weight loss pill seem to do what it claims to do? Sure. Okay. Looking at this, it seems like, yeah, you know what? Consistently, everybody who's taking a pill seems to be losing weight. Okay. And not dramatic amounts, but everybody's losing about 5 to 6 pounds. Okay. Well, what happens? Okay. We're going to do this the wrong way, which is treating the groups as independent. Okay. we did this, what if we analyzed this using what we learned earlier today, doing just a plain old standard t-test, okay? What you would need is you would need the mean of group 1, the mean of group 2, the standard deviation of group 1, and the standard deviation of group 2, right? And then you have n, you've got 5 in each group. So let me just punch these numbers into the calculator and get the mean and standard deviation here. No. Computer is broken. What do I have? 190, 220. Call them out for me, please. One.
140, 160, 240.
Okay, so the mean of that column is 190, and the standard deviation is 41.23. Okay, and then column 2. I've got 185, 214, 136, 155, 234. Okay, and the mean standard deviation is 184.8 and actually 41.23. Okay. Okay, so we have a null and we have an alternative hypothesis. The null is that the difference of before and after is nothing, that the weight loss pill does nothing. And what is the alternative? Do we want a directional or a non-directional one? We want directional, right? We want to see if the weight loss pill actually causes people to lose weight. So mu1 minus mu2 should be greater than 0. And what do we see? 190 minus 184.8. This is my observed difference. A difference of 5.2 pounds. Okay, is that large or small compared to what we're getting? So our test statistic is what we observed, 5.2 minus what we're expecting. We're expecting a difference of 0 if the null hypothesis were true. If the weight loss pill did nothing, we would expect a difference of 0. And the standard error, 41.23 squared over 5 plus 41.23 squared over 5. What is that? Where did my calculator go? There it is. It's so painful to watch my own videos. It's like, it's just cringeworthy. Okay. So I get a standard error of 26.1 or something like that. Okay, and I do 5.2 divided by that. I get a test statistic of 0.1994. Test statistic of 0.1994. I would have 8 degrees of freedom. Everyone with me so far? Okay, so what is the p-value that I get here? Well, I go to my t-table. I'll go to the row 8 degrees of freedom. And the very first number is 0.889. And then the next number is 1.397. Okay, and I'm observing a test statistic of 0.1994. Okay, so 0.1994 is a lot less than 0.889. Well, I don't know whatever a lot is. Okay, so if I draw a line at 0.889, I've got 20% here. But I'm drawing a line at 0.1994. So practically 0.2. So whatever it is, the amount in this tail, it's a lot more than 20%. I don't know exactly how much it is, but it's certainly more. It's greater than 20%. We also know it's less than 50%, but we know our p-value is bigger than 20%. We don't know exactly what it is, but it's bigger than 20%. So we would say we do not have evidence to reject the null hypothesis. Are we in agreement with that? So we don't have evidence that the weight loss pill works. Okay. This is what we would conclude if we treated these as independent groups. Is that right? Okay. But that's not the correct way to do it. So what we're going to do is we're going to treat them as paired data. So this is what happens when you treat them as paired data. I just want to make sure that this is okay with everyone. Just, yeah, okay. Sometimes you guys are quiet. Just a little head nod. I feel good. All right. What we're going to do is we're going to look at the difference created. What is the difference? Okay. And so we create a third column called the difference, and we just do 190 minus 185. So here I get a difference of 5 pounds, 6 pounds, 4 pounds, 5 pounds, and 6 pounds. So, as paired data, okay, this is the correct way. For paired data, we're just going to look at the difference column. So you create the difference column. Okay. And then that's the only column we care about now. And our null and our alternative hypotheses is now this. It's no longer mu1 and mu2. It's, is the true difference, is that equal to 0? Or is the true difference not equal to 0, greater than 0, or less than 0? In our case, what do we want? Greater than 0, okay? So is the before before weight greater than the after weight? Is the difference of before minus after, is that greater than 0? This is our hypothesis here. Our observed difference, so what did we observe? Our observed difference would be d bar, okay? So the mean difference here. So I just do 5 plus 6 plus 4, whatever this is, okay? That's going to be 5.2. And then my standard error here, what is my standard error? It's going to be the standard deviation of the differences divided by the square root of n. But n is now the number of pairs, or n is the number in the difference column. Okay. So the standard deviation here is going to be a lot smaller, right? Because here I'm going 4, 5, 5, 6, 6. So the standard deviation is tiny now. I'll tell you what that is. 4, 5, no, I'm sorry, 5, yeah, 4. Okay, the standard deviation, S sub d, is 0.8367. Let's just round up to 0.84. And we're going to divide by the square root of 5. So my standard error is really tiny now. 0.376. So my test statistic is my observed difference, 5.2, minus my expected difference of 0, divided by my test statistic of 0.376. Or not test statistic, standard error. Okay, so now I have a test statistic of 13.8. So that's huge. And if we look this up in our t-table with 8 degrees of freedom, okay, 8 degrees of freedom, I'm sorry, not 8 degrees of freedom, 4 degrees of freedom, 4 degrees of freedom. Thank you for catching that. So 4 degrees of freedom, I look over here, and the most extreme it goes is 4.604 and 8.610. And this is 0.00005 and 0.0005. Alright? And so this is 8.61 standard errors away from what we expect. I'm 13.83, so I'm way out here, okay? So again, I have no idea what my tail probability is, but I do know it's certainly less than 0.0005. And this is going to be my p-value because it's just one-tailed. So whatever my p-value is, I have no idea, but it's certainly very, very, very small. And so now I can say I'm going to reject the null hypothesis. We have evidence that the weight loss pill works.
Are there any, like in an instance, if say you're doing an experiment and someone drops out before the after, do you just get rid of their entire data, or?
Yeah, because they have nothing to pair against.
Mm-hmm.
If you're doing a before and after, okay. So yeah, sometimes that happens. It depends, okay. The rules are different if you're dealing with time series, but we're not going to cover time series in this class. Okay? It just gets a little too complicated. So. But yeah, for paired data like this, if there's no pairing, then they're not part of the data set. Because we would have no idea if they actually gained weight or lost weight or something like that. Yeah. So yeah, so how are we getting such a significant p-value here, whereas over here we got nothing, not significant at all? What's going on there?
As if they have nothing to do with each other.
Okay, so what's going on, okay, so remember the p-value is what is the probability of observing your data or something more extreme if the null hypothesis were true. Okay. And to decide the probability, we are asking how unusual, we observe a difference, how unusual is this difference compared to basically the internal variation within our data. Okay. So here we did, the difference in both cases was 5.2, and the thing that changed significantly was the standard error. Okay. When we treat them as independent groups, what's happening is that, you know what, across the board, people are losing, 4, 5, 6 pounds. Okay, everybody's losing that. But the variation that exists between people's starting weights is so huge that this 5 pound difference is just lost. Okay, it's kind of lost within the variation between people's weights. Okay, everybody's different. Their starting weights are different. That 5 pound difference, 4 or 5 pound difference, it's just lost. It's not seen as anything significant. Okay, and that's what happens when we compare these two groups. By pairing the data, okay, we're saying we started off at 190, we ended up at 185. We get a difference of 5 pounds. By pairing the data, we isolate those differences and we see that everybody has lost 5 pounds, 6 pounds, 4 pounds, something in that ballpark. Okay? So everybody across the board is losing weight. Not a ton, but it's very consistent. Okay? And the paired data allows us to zero in on the difference, okay? And by pairing it, we've taken into account everybody's individual differences between each other. Whereas when you treat them as independent groups, we're just grouping this all as group 1 and group 2, and that difference is lost. Okay, so that's what's going on there. Okay, so so you got a few homework exercises. Next week's quiz, you're going to see a paired data question, and then you'll also see a regular independent data question. The quiz is easy. It should be very easy to tell which one is paired and which one is not. Well, I don't know. Should I make the quiz harder? And make it I don't know, because in the final exam, I don't say this is paired and this is not paired. Okay, it's a little bit tougher in that regard. So I had students kind of tell me like, oh, the quizzes are too easy and the final was too hard. I don't know. I didn't think the final was that hard, but well, anyway, people will complain about it. So, all right. Anyway, that's it. Have a good week. See you guys next Thursday.